So let us solve two more numericals on dimensional analysis. This is another problem on your book. The problem says that the critical velocity Vc of a liquid flowing through a tube depends upon the coefficient of viscosity eta of the liquid, the density rho of the liquid, and radius r of the tube. Using the method of dimension, obtain the formula for the critical velocity. Like the previous sum that we were doing, we will write that critical velocity is proportional sum eta to the power x, rho to the power y, and r to the power z. And then we will substitute this with a dimensionless constant k times eta to the power x, rho to the power y, r to the power z. Now, what is the dimension of critical velocity? The dimension of the critical velocity, after all, it's velocity, so that is meter per second. What is the dimension of eta? Eta is basically the coefficient of viscosity, and the coefficient of viscosity has the units of kg per meter per second. So the dimension that it has got is m, l to the power minus 1, t to the power minus 1. Dimension of rho, density, is known to you, it's kg per meter cube, so m, l to the power minus 3, and the dimension of radius r is equal to l. Now what is the LHS? Well, LHS is basically L t to the power minus 1. This is our left hand side of the equation. And what is the RHS? RHS is eta to the power x, that is m, L minus 1, t minus 1 to the power x. Then rho to the power y, that is m, L minus 3 to the power y, and r to the power z, that's L to the power z. M to the power x plus y, L to the power minus x minus 3y, t to the power minus x, and yeah, L to the power, there will be a plus z here. Now we use the principle of the homogeneity of the dimensional analysis, and using that we shall find out the coefficients. So we get x plus y to be equal to 0. We get minus x minus 3y plus z to be equal to 1, and we get for time minus x to be equal to minus 1. So from here x turns out to be 1. Once we get x to be 1, if we substitute the value of x in the first equation, we get y to be minus 1. Substituting these two values here, what do we get? Minus of x is minus 1, minus 3 into minus 1, that's plus 3. Plus z is 1, so that gives us z equal to 1 plus 1 minus 3, that's minus 1. So we see that the critical velocity is some constant times eta to the power x, that's 1, rho, that's density to the power minus 1, and radius to the power minus 1. So the equation looks something like k eta by rho r. So the expression for critical velocity is k eta by density times radius. Again, what is this k? It is a dimensionless constant, and as I said, this is one of the drawbacks of dimensional analysis, that we cannot find out what is the value of the constant. But as you shall study later in fluid mechanics, this k is something called capital R, which is the Reynolds number. You shall be studying this when you do viscosity. One quick last problem. Let us do another problem. So what does this problem say? The question says that if force, velocity, and time are taken as fundamental units, that is force, velocity, time are considered as fundamental units, like instead of mass, length, and time, if we take force, velocity, and time, what will be the dimension of mass in this new system of unit? This is another kind of problem you can get. What will be the dimensions of mass in this new system of units? So these are hypothetical system of units. We know there is no such system like force, velocity, and time, but if there were, what would be the dimension of mass in that system? Like we know the dimension of force in the system of kg, meter, and second. So what would be the dimension in this case? Well, you have to do something like this. Just like the previous expression, you take that mass is some dimensionless constant times force to the power a, velocity to the power b, time to the power c, and then you write down the dimensions. For mass it is simply m to the power 1. For force it is kg meter per second square to the power a. For velocity is length per time to the power b, and for time it's simply time to the power c. And then if you equate units on either side, you get this becomes k times m to the power a. You get L to the power a plus b, and you get time to the power minus 2a minus b plus c, and on this side you have got only m. So you on computing both the sides, you can easily see that a turns out to be equal to 1, then a plus b is 0, a plus b is 0, and since a is 1, that means b is equal to minus 1. And then there's another equation, minus 2a minus b plus c, that is again equal to 0. A is 1, so minus 2, b is minus 1, so plus 1, plus c equal to 0. So c is equal to again 1. So from there, therefore we can write that the dimension of mass in this new system is force to the power a, that's 1, velocity to the power b, that's minus 1, and time to the power c, that's plus 1. So basically it is f v minus 1 t. So this is how we write down the unit in some hypothetical system of unit. These are certain sample problems of the dimensional analysis that we solved. There are obviously lot of more problems present, but solving these sample problems shall be enough. Now you practice more of the problems as you find in the exercises and examples of your book, and if you face any doubt, let me know, we will discuss it.